Okay, so in this talk, I want to address three fundamental ideas. The notion of deterministic, the notion of random, which I will explain in the talk, I will also call sometimes statistical, and I will explain what that means, and also the notion of non-statistical, right? So I hope that by the end, everyone has maybe some ideas of what these things might mean, but I hope that by the end of our reflection together, we will have understood these three concepts in much more depth. We will see if this talk has helped for something. So the first question really is, what is the difference between deterministic and random, right? And I think as a simple example, I want to talk about flipping a coin, right? So we all know what flipping a coin is, right? You take a coin, you flip a coin, you get heads or tails. So now comes my first question to all of you, right? People in the room, people everywhere. So online, I would like to ask everyone to put their hands up if they think that flipping a coin is deterministic. Hands up if you think flipping a coin is random. Yes, but I saw lots of people that did not put their hands up for anything. I think you have to make a choice here. You know, sometimes in life, you have to make a decision and make a choice, right? So let's start again. So you have to choose one or the other, okay? So if you're online, you can raise your hand. You know, you can do it also without the camera. There's a thing. Okay. So raise your hand, everyone who thinks it's deterministic. Hands raised. Okay. You need to decide one or the other. In the room, I don't see. Is there anybody raising the hand in the classroom? I still see lots of people. Okay. How many people think it's random? Okay. Well, I think a lot of people are afraid to vote. But what is interesting is that some people, you know, usually when I'm in a classroom live and I ask this question, about half the people say it's deterministic and half the people say it's random. And if you think about it, that is very strange, right? Because we think of deterministic and random as being opposites of each other, right? Just general feeling. So I asked this question without first formally defining these notions, right? And someone is saying, is the act of choosing one of these to answer deterministic or random? This is a much more philosophical question that we will not get into. But the decision somehow is interesting because we've not defined exactly what we mean by deterministic or random. Right? And so somehow part of the reason why there's different opinions maybe is to do with the different definitions of these words. As you know, in mathematics, the most important thing is define exactly what you mean, right? So let's think about what we mean by this, right? So often, often this dichotomy between deterministic and random is interpreted as a dichotomy between predictable and unpredictable, right? So let's think a little bit. So sometimes we think of deterministic as meaning predictable. Sometimes we think of random as being unpredictable. So let's think a little bit about this dichotomy first of all. So there are many physical phenomena that are predictable, even some very complicated physical phenomena. For example, the motion of the planets, as you know, is very predictable, right? Amazingly, because the motion of the planets seems like a very complex physical process, right? There's very complicated forces of gravity and so on, but it's very predictable. Even the ancient ancient civilizations, they knew how to predict eclipses and motion of the planet and so on. Even if you just throw something, if you throw an object, it's fairly predictable, not exactly, but otherwise we could not play football or tennis, if you had no idea where the ball was going to go. So there's a certain level of predictability in this, right? On the other hand, there are other physical phenomena that are not very predictable. The weather is a very classic phenomena. The weather is, we cannot say exactly next week at what time exactly it's going to rain, or, what's going to happen. And also, turbulent fluids, or simply flipping a coin. As we said, the amazing thing, flipping a coin seems like a very simple physical phenomena, but it's not predictable, right? So all of these systems are physical systems, right? They all obey the laws of physics. I think we must all agree with this, right? The laws of physics are laws that determine certain forces that occur. When you flip a coin, you're applying a force, right? And the laws of physics determine how many times you flip the coin. So the question is, why are some of these phenomena predictable and some are not? Since they're all physical systems that satisfy the laws of physics. And of course, I'm not the first person to ask this question, right? So a much, much, much greater mathematician than me, who you must have all heard about, Henri Poincaré, he asked exactly this question, right? He said, why is it that storms or the weather seem to come by chance, so that many people think it is natural to pray for rain or for fine weather, though they would consider it ridiculous to ask for an eclipse by prayer? Right? So he said precisely this. Why is it so different? Why is the weather so unpredictable and the motion of the planet so predictable? Right? Why? So we're going to discuss this a little bit, and we need to take a step further back to the 1600s and early 1700s. So I'm sure you've all heard of Leibniz and Newton. They were two of the greatest mathematicians of all time. One was German, one was British. As you can see, they lived almost exactly the same time, right? And they're both credited in some way for being the inventors of the calculus. That is every school, every university student's nightmare, right? But also, the foundation basically of most of modern mathematics. And they were in very fierce competition, as you might know, right? They were really competitors. I think now I think it's funny to say, when you look at their photos, I think probably they were also competing for the best hairstyle, right? Who do you think wins the best hairstyle? I think Leibniz probably wins on that, actually. But I'm not sure if they thought about that so much. Anyway, the calculus, as you know, gave rise to the theory of differential equations, right? Is the foundation in essential differential equations. And differential equations are exactly models of the way systems evolve according to physical laws, right? So the equations encapsulate the physical laws of the system. And then the solution of a differential equation is the evolution of the system of a certain initial condition under these physical laws. And this idea of differential equations gave rise to the kind of philosophical idea of determinism, because mathematically, as you know, one of the fundamental results of differential equations is that under some very mild assumptions, you have existence and uniqueness of solutions, right? This is the fundamental theorem of differential equation. And what does uniqueness of solution means. Think about it not just from a technical point of view, but uniqueness of solutions means that once you fix the physical laws, which is a differential equation, and once you choose the state of your system, so the initial condition, then the physical laws, the full uniqueness of solutions mean there's only one way to go according to those physical laws. That's what uniqueness means. It's very important. It means the solution is the evolution of the process, has only one possible evolution that is fully, completely determined by the physical laws and the current state of the system. So this was, when the mathematics of differential equations gave this, and the idea was that differential equations were modeling the real physical world. It became at the time in the 18th century, and also 19th century, a big debate. Does that mean the world is fully deterministic? Do we have any free will? We will not get into that in this conversation here. But the question is, could we, is the world deterministic, and what does determinism mean? Everything is determined somehow. And this idea was very much well described by another great mathematician called Laplace in the early 19th century. And he explained this concept of determinism that says that the future evolution of a system is completely determined by the physical laws and the initial condition. What I just said. Again, please raise your hand or ask a question if you have any comments or clarification. I always see these talks as an opportunity for a discussion instead of just a lecture, right? So let me know if you have any questions. So this was the concept of determinism, right? So we talked initially about what is the definition of deterministic. This is at least, and I'm saying this is not completely obvious what it means, but the idea of differential equations help to give precise meaning to the notion of determinism. But Poincare himself made a very interesting remark, right, about this. And he says, look, a system might be deterministic, but it may happen that small differences in the initial condition produce very great ones in the final phenomena. So this is a very subtle point, right? To say, okay, suppose we have a world where everything is deterministic, or suppose you just have a differential equation so that given the initial condition, the full evolution is completely determined. But now take a different initial condition, very, very close to the first initial condition. Does that mean that the evolution of that initial condition is almost the same as the evolution of the first initial condition? These two things are not the same thing. To say that identical initial conditions have identical evolution, or that nearby initial conditions have nearby evolutions. And we're going to look at an example. So this, first of all, this idea remained as a very, very kind of abstract idea, that people understood this idea for a long time until the 1900s, where a meteorologist called Lorentz, he started studying particular system of differential equations, which are now called the Lorentz equations, in the 1960s, and he started studying them with a computer. Now, in the 1960s, computers were very primitive, very basic, right? This was his state of the art. This was the smallest, most compact computer you could have at that time. And of course, this computer did not have graphics and so on. You had to use numbers, punch cards. I'm not exactly sure how. But he studied these equations, which is a system of ordinary differential equations. And he wrote a paper. He discovered something very interesting. And he wrote a paper that has become, a milestone paper called Deterministic Non-Periodic Flow, right? And in this paper, I don't know if you can see the lighting, it's quite small. He shows deterministic ordinary nonlinear differential equations, right? So he shows these are nonlinear differential equations which are deterministic because they satisfy the condition of uniqueness of solutions, but slightly differing initial states can evolve into considerably different states, right? So he exactly showed the system that exhibit this phenomena that Poincare was talking about, right? And he called this sensitive dependence on initial conditions. Sensitive dependence means you change the initial condition a little bit and things can change a lot. And now we're going to do a little bit of mathematics together and look at a very simple example of a mathematical model that has this property, just to understand a little bit how this works, right? So we're going to look at the dynamical system, which is the field I'm working. My favorite dynamical system that all my students know very well. And it is this function here called f of x equals 10x, which means you multiply by 10 and then mod 1. Right? So what does mod 1 mean? Mod 1 means you only consider the decimal part. So it's if you take a number that is bigger than 1, you just take the fractional part, the decimal part. Right? And then you iterate it. So you can think of this is not a differential equation because it is a discrete step dynamical system, but it's very similar in mechanism. So you start with an initial condition and you just apply the map over and over again, and there is a certain kind of evolution of the system, right? So let's try it together. So let's take just some arbitrary number that I've just put there. So as you know, all the real numbers have infinite decimal expansion, right? Some of them have the decimal expansion that at some point is all zeros. Some of them have decimal expansion that at some point is all 1, that is periodic. Some of them have decimal expansion that is not periodic, it repeats. It does not repeat, right? Everything has a decimal expansion. But of course, I cannot write down the full decimal expansion, right? So I'm just going to write down the first 6 decimal places, right? But if you think about it in practical situations, usually 6 decimal places is a very precise measurement, right? If we do something with 6 decimal places. So what happens when we apply this map to this point, right? Does anyone know anyone sitting in the room in University of Peshawar right now? Can you tell me when you multiply this number by 10, what do you get? You all know what to multiply by 10, right? So to prove to me that you're not sleeping, someone actually has to answer this question. So someone online says 36.2519, which is not correct, unfortunately. Yes, exactly. Can someone tell me in the room? Come on, don't be shy. Someone is online, but I would like someone in the room. Do we know? What about these 2 girls in the first row here with the white hijab? Yeah. How do you multiply by 10? So multiplication by 10 is the easiest multiplication, right? This is my favorite system, okay? So when you multiply by 10, all you do is you shift the decimal place. Do we all agree with that? Good. So multiplication by 10 is very easy. So when you multiply this number by 10, you get 3.62519. We all agree? Let's make sure we agree because Okay, so, but now we take mod 1, right? So mod 1 means that we only take the decimal part, right? Mod 1 just means drop the integer part because we want a number between 0 and 1 every time, right? So when you multiply by 10 and you take mod 1, you get this number here. Do we all agree? So we've multiplied by 10. So we switch the decimal place. We get 3.62519, and then we drop the 3 and we get 0.62519 something. Okay, this is very simple, but it's important that we all that we all understand. So now let's do it again, right? So let's do it again. So we multiply by 10. We do it again. We move the decimal place and we drop the 6, right? So we get 0.2519. Everyone agree? Yes. Okay, so now we can start going a little bit faster because we understanding this, right? So the next step will be 0.519. So you can see here, I'm indicating here, you start with an initial condition x. F of x means that we've applied this map. F2 of x, which means that we've applied it twice, right? And F3 means we've applied it 3 times. So we are constructing a kind of evolution of this initial condition, right? We started, this is the initial condition. After 1 unit of time, you can think of this as the physical modeling, the physical process in some sense, right? That's the law of evolution, which is in the differential equation, is the differential equation. In this case, this is the law that is telling you wherever you are, what's your next step is going to be, right? So now that we are here, the next step is going to be this step, right? And then the next step will be this step, right? What will be the next step? Will be 0.9. And then what? What's happened? What is this point going to be? Can someone tell me where are we going to be, right? This point is bouncing around from 0.36 something, 0.62 something, 0.25, 0.5 something, 0.19 something, 0.9 something, and then what's happened here? Okay, someone is suggesting 0. Is it 0? It's approaching 0. Someone is saying it's approaching 0. So why do you think it's approaching 0? What is exactly that point? It's approaching infinity. Someone is saying, okay, I'm glad there's a nice discussion here. Great. So 0, 0, it's approaching 0, it's approaching infinity, 0.9. Ah, now this is an answer I like. We need to know the next digit. We need to know the next digit, right? So what can we say? How can we say it's approaching 0, it's doing this, it's doing that? The point is, yes, it's 0 point something else. So if we knew the next digit here right from the beginning, right? If we knew what digit this was, suppose this digit is a 4, right? If this digit was a 4, then we would carry this 4 through here, and here we would have 0.4 something, right? And then suppose we had, and then of course at the next step we were in the same situation, but if we know also the next digit from there, we would also know that. So the question is the evolution of this initial condition deterministic or random? So clearly if I was there, we could have more of a discussion about this, but being online, so clearly this is deterministic, right? Because if you had all the infinite decimal places, you would at every step know exactly the infinite decimal places, right? So you would not lose any information, right? You got to the sixth step, you would still know all the infinite decimal places. And if you think about it, whether you know them or not does not matter to the system, right? I mean, you don't know the decimal places, but they are there if you assume that a number has been fixed, right? Even though we do not know the decimal places, there is a number, it has an infinite number of decimal places. The full evolution is completely determined by the decimal places of the number, right? Because you can see how this works here, right? So the fact that we cannot predict what happens at this stage is simply due to the missing information that we have about the initial condition. Is not due to the fact that the system itself is intrinsically random or unpredictable in any way. But if we know only a finite number of decimal places, at some point, as you can see, to understand what happens, we will need to know the other decimal places, right? So if we take a small, suppose we took a slightly different initial condition, like these two initial conditions are almost the same, right? This is 3.62519, 0.362521, right? If you're a carpenter and you're building a cabinet, right, and you're trying to measure the length of wood that you need, you're not going to measure to this level of precision, right? You're going to think, well, these are really the same things, right? They're very precise. But suppose you are using this to model some physical phenomena, right? This is the real initial condition, but this is your measurement. You make a very tiny mistake in your measurement, right? Very tiny mistake. The first four decimal places are the same, it's almost the same. And then you use this model to try to predict the evolution of this system, right? So you see what is the next step here, right? So it's very, very close also. So again, you multiply by 10, you get this. Then we do the same thing that we did before, right? 0.2521. These two are still very close, right? These two are still fairly close. So you started with two close by initial conditions. They're still fairly close. This is not so close, but it's still fairly close, right? But what happens at the next step? Suddenly, you're not so close anymore. Look at this. Amazing, right? So you started with two initial conditions that were very, very close, indistinguishable almost, you could say. And within only 5 iterations of your system, one of them gives, this is are all numbers between 0 and 1. So 0.1 something and 0.9 something are almost as far as you can get, right? So this is exactly sensitive dependence on initial conditions. So this shows that even if two initial conditions are very close, then after a short amount of time, the evolution of the system of a deterministic system can be very different. So that's why I think it's a very nice example, because you can see this very well. And the Lorentz equations that were studied in the 60s that I said, basically they have sensitive dependence basically for the same principle. Right? I will not go into it now, but it's basically the same mechanism. And also, when we talk about flipping a coin, when we go back to flipping a coin, right? And if you think about it, flipping a coin is also deterministic, as we said before, because you're applying a force. But the problem is that the mechanism that we use to apply a force, if you think about how you actually flip a coin with your hands, the actual mechanism you use, it is very difficult to control exactly how much force you're giving. It's almost impossible to control exactly how much force you're giving, right? if you if you could control exactly how much force you're giving, if you always gave exactly the same force, the number of times the coin would flip would be always exactly the same, and you would be able to get always exactly the same thing. And you could win lots of money because you could get people to bet and you could control what heads or tails you could get, but you cannot control it. And just if you give a little bit, 5% extra force, then it will flip one more time and you will get tails instead of heads, and you cannot control it, right? So the flipping a coin has sensitive dependence on initial conditions, right? That's why it is unpredictable in exactly the same way. Yeah. So let's summarize, going back to our questions, right? Is that some physical systems have this property for some reason of having sensitive dependence on initial condition, and the unpredictability or chaos in some physical systems like flipping a coin or in the weather, in the turbulence, is simply sensitive dependence on initial conditions. It's not randomness. It's a deterministic system with sensitive dependence on initial conditions. Whereas other physical systems like the planet, just because of the physics of the system, do not have sensitive dependence on initial conditions. And therefore you can predict. And that's because we have only one sun. I don't know how many of you have read, there's a Chinese book, a Chinese series called The Three-Body Problem. Maybe some of you have seen it, which is precisely telling the story of a universe where they have two suns, and this makes everything very unpredictable, chaotic in exactly the same way. This is a reference to a physical issue, right? That makes, in some cases, even the motion of the planets very unpredictability. So the conclusion to this first half of my talk, let's say, is that the message that I would like to convey is that the unpredictability and the chaos that we see in some systems are perfectly compatible with determinism, right? First of all. So determinism does not mean predictability, is the most important point, right? So one of the um, interesting. So now I want to, let's say, in some sense, this addresses this issue of the concept of determinism. Then there's a natural question that comes up, right? Which is the word random. Going on to the meaning of the word random. Generally, the word random, what's the difference between the word random and the word unpredictable? Do you have any sense? What's the difference in the meaning that we usually associate to these two words? Why do we say that flipping a coin is random and we don't just say flipping a coin is unpredictable? Why do we use that word? Random means the output is from a set of possible results, but also flipping a coin is the output is heads or tails. So we could just say it's unpredictable because we cannot tell if we get heads or tails. Because we have two conditions, there's the same answer. We have two conditions in the flipping coin, but we can say just as much as that it's unpredictable which of these two conditions we have. Yes, I see a hand raised there in the room. Yes, please.
Okay. So the question that you asked is basically the difference between random and unpredictable. So basically, like in probability, when we are talking about an event which is random, right? So flipping our point, right? We can predict the outcomes because definitely it's not unpredictable totally, like in terms of probability, but random depends on like how perceive an event, right? So, like taking a random person from the whole audience will be considered random because I took a certain person without definitely thinking about the future outcomes, right? So that definitely how we perceive the term random, right? Not mathematically or technically, just expressing how we perceive the term, right? How we go for the terminology random.
Yes, yes,
And
this is
if
my question. What do we understand by the word? Yes.
random means taking something that we don't know or which is not specific, right? That is random. And unpredictability is certainly or somehow related with the term event. Like the weather, it's unpredictable, but like the results in cricket, it's unpredictable. But somehow we can actually predict some of the portion of the event.
Okay. Okay, thank you very much. Thank you very much. I don't know your name, but thank you very much. Is there anyone else who'd like to say? I see Atik online has raised his hand. Atik.
Sir, I will say that in randomness we will know that the output will be from some set, like in case of coin, we know that the output will be head or tail, but in unpredictable we don't know the output of the experiment what it will be. I think so.
Okay, so those are all interesting comments, so this issue about the outcome being, so I would say that we can easily say that a coin is, so there's someone else. No, did you want to say something? No? Yes? No?
Yes, hello. I was saying that if the system has a law or a pattern that that governs the outcome, even if we don't know the initial condition, it's not random. It's undeterministic because we don't know the initial condition. Just like the example you gave us. So the first number we started with, if we don't know how it ends, we can't know what's the outcome. But if we know, we can calculate the outcome. So it's not random.
Well, we're trying to understand, that's a good point. We're trying to understand what we generally mean by random and why we often use the word random in systems that, as you correctly say, are not random.
Random, like quantum events are random because we don't know how they behave.
Right. Let's see. So I think Tamina, did you also want to say something? Yes.
Yes, I want to say random just if we don't see mathematically, because mathematically random mean noise. If a system has noise, then it means system is random. But if we just focus on the word random, it means it doesn't have any order or pattern. And unpredictable means we don't know the outcome. So in unpredictable, we don't know the outcome, and in random, we mean a system doesn't have pattern or any order, means it has noise.
Interesting. Okay, there was, I think someone else put their hand up. So thank you very much for all these interesting. Is there someone else wanted to say something? HP?
Hello, Stefano. I think by randomness, we mean that there are some phenomena or some systems that things occur from nowhere randomly. They occur like by its very nature of the phenomena, not because of some systematic fault. For example, if I have to record a voice of a same person 3 times, So the voice may look same to us, but there may be different type of variations in the recording, and the recording curve will look there will be a lot of variations in the curve. So this is not because of some the system fault or other thing, but it's because of by its very random nature. So I think that is the difference between an unpredictable mean that we cannot predict it. We don't know the output of what will happen.
Okay. Okay. Thank you so much, everyone. So I'm going to give you my own interpretation answer to this question. So I want to emphasize here that all the comments were very relevant, right? So I'm not giving any strict mathematical definition here. We're talking about what we generally mean by these words when we use them, right? And out of, I would like to, I guess I personally most aligned with the first comments that brought up the concept of probability, right? And if we really try to address the specific question as to instinctively, why do we say something is random instead of unpredictable? In my sense, is that usually we give the word random some additional properties with respect to unpredictable, a little bit more structure, right? And often, in many of these systems, a very interesting observation is that the long-term averages are often statistically predictable, right? So, for example, as you know, when you flip a coin, until now I've emphasized the fact that we don't know the outcome. But if we flip it 100 times or 1,000 times, empirically, we see a result that we get very close to 50% heads or 50% tails, right? But if you think about it carefully, why should we get 50% heads or 50% tails? We take it for granted because that's what happens. But if you ask yourself why, it is not obvious at all. Why? Each time you flip it, we have no idea what's going to come, right? And as we said before, if you could actually control exactly, if you put a little machine that gives exactly the same force in the same place, you will always get the same outcome. In that case, you would not get 50% heads or 50% tails. You would just get always the same heads, or tails, you get what? So the question is, why? Since every time you're making a little mistake or whatever, you cannot control it, why does it get close to 50%? It is very non-trivial question, right? And similarly with the weather, the weather is unpredictable, but the averages, the long-term averages are very stable and very predictable. The average temperature in Peshawar in January. Every year, the average temperature in January will be very similar, the average, right? The averages. But which day exactly you will get, or the average amount of rain, right, will be very similar. So the averages are very stable. And this is very interesting. And often we use the word random to include this property, this idea, because when the averages are stable, we can start talking about probability, right? Why do we say that there is such a thing as a probability of getting heads or tails? What does it mean? It means nothing if you don't know that if you flip something 100 times, you get 50% heads, 50% tails. And we use that as a way to define, to say, well, the probability of heads or tails in practice is 50%. We're extrapolating, we're using the word probability in a way that's not very precise to say, okay, I know that if I do this many times, I will get this proportion of things, right? So how does this apply in mathematics, right? So I'm going to get a little bit, I'm going to put one formula here, and I'm going to say that even in mathematics, we can ask whether these long-term averages are stable or not, right? So for example, in the map that we looked at before, this map 10x mod 1, there is a theorem, a mathematically rigorous theorem, that says that almost every orbit has the same statistics. So the statistics are very stable. So what do we mean by statistics, right? So I'm going to spend a little bit of time thinking of that. So, most of the talk is not very technical, but I'm just going to put one formula. Imagine here you have, this is the interval between 0 and 1. This is some arbitrary point that I've chosen. This is some arbitrary interval, right? And I would like to ask a question. What is the statistics of the times that the orbit of X, the evolution of X, enters the interval A, right? Because as I said before, if I know the full decimal expansion of X, I know exactly where it goes, and I know exactly how many times it visits A, because I know exactly when it's in A. But if I don't know the decimal expansion, it becomes very difficult, very unpredictable, right? But what are the statistics? So this is the key formula, right? And I want to spend just a few seconds looking at this formula. What is this formula saying? So look at this part of the formula here, right? This formula is saying that after the kth application of the map, you're inside A, right? And if you look at the numerator, what this is saying, this is the set of k's such that fk of x belongs to A. And this here means the cardinality of the set of k's. So what this is doing is simply counting how many times you fall in A, right? Because this is the set of all k's when this iterates of x are in A. This is just counting between k equals 0 to k equals n. So this numerator here is a number between 0 and n, right? Because if up to time n you never fall inside A, then it will be 0. It could also be that up to time n you always are inside A. In that case, this would be n, right? So this is an integer number between 0 and n, right? And when you divide by n, it means you're taking the proportion, right? So you're looking at the frequency of how many times. For example, if n is 100, right? And if you fall inside A 50 times, right? Then on the numerator you have 50, on the denominator you have 100. 50 over 100 is 1/2. So that means you spent half your time in A. Is that clear? Any questions? So notice, of course, that this number depends on n, right? When you change n, this number will change. This is a number between 0 and 1, right? When you take n equals 100, you will get a certain number. When you take n equals 1,000, you might get a different number, right? Because it could be that up to 1,000, you spend a different proportion of time in here. When you take 1,001, as you change n, you take n bigger and bigger, this number may change. It's always a number between 0 and 1. And then the question is, Atik, you have your hand raised, yes?
Sir, if we define, let we define our x like a random variable, like it's the output of some experiment. So our k is continuously dependent on x. If we are changing x, our k will change between 0 and n.
Yes, but this is introducing concepts when you say it's a random variable from some experiment. We're introducing concepts that are non-trivial, right? And to understand really what it means to do these things, let's be a little bit more basic, right? So there's a lot of interesting things you can say with sophisticated mathematical tools. But now let's think of literally just choose one x, or you're given one x, right? And you look at the orbit of x and you compute these numbers, right? Which for every n tells you which proportion of time you spent inside A. Okay, this is just a set of numbers that depends on your interval A, and it depends on your point X, of course. If you take a different point X, you will get a different number of times because it will have a different evolution, right? So when you have this sequence of numbers depending on n, what do you usually do? What have you been taught to do whenever you have a sequence? What's the first question that you ask about this sequence? When you hear the word sequence, what's the first question you ask? Okay, this is a sequence. And you say, yes, general term formula when you're used to very explicit formulas, but here we don't have any formulas, right? We cannot have any formulas. So limit. This one you're not allowed to answer. So generally, you're given a sequence of numbers and you ask, is there a limit? Right? In other words, does this sequence converge? Right? So I presume you all know, or you've studied, or you should know what the limit of a sequence is, whether it converges or not. And so you ask whether this limit exists. As you know, sequences do not necessarily have a limit, okay? But this theorem, highly non-trivial theorem, says that this limit exists for almost every point. So I will not discuss this, but there is a natural measure called Lebesgue measure here. Almost every point with respect to Lebesgue measure, which means that the set of points for which this limit exists has zero measure, so it's a very small set of points. Not only that, but this theorem tells us also what this limit is. And what this limit is just as amazing as the limit exists. And the limit is exactly the length of the interval A. So all these points have the same limit. So what does this mean? This means that even though X jumps around a lot all the time, the frequency of visits to A converges to something. Okay, so the fact that it converges to something is really something very remarkable, because it means when you take n very large, suppose you see that this orbit is spending about 10% of its time inside A, the amazing thing is the longer you wait, and it will stay close to 10% all the time, right? This is a bit like saying that when you flip the coin, the more you flip the coin, the closer you will be to 50%, right? And you're getting closer and closer to 50%. So the convergence of this limit is really something quite remarkable and not obvious at all, right? And what this says, so this is just this, so Lebesgue, almost every point, visits every interval A with a frequency which is the measure of A. So in some sense, this is a crucial point, and this is, I think, was said by the girl in the room there that was first talked about random as related to probability, is that it is exactly the convergence of this which allows us in some sense to talk about the probability, right? Because if we know that this limit exists, then we say, okay, as we said before, we don't know exactly where this point will be after 1,000 steps, because to do that, we would need to know 1,000 decimal places of x. We don't know 1,000 decimal places of x. But the amazing thing is that even without knowing anything about the decimal places, we can say that the probability of being in A is 1/10 or whatever the length of A is, right? Because we know that it spends 1/10 of the time inside A. So just to conclude, this is in some way we can see the deterministic system as being random, right? So my conclusion here basically is that when we say that a deterministic system is random, like when we use the word random, talking about flipping coins, sometimes not completely consciously or unconsciously, we're really thinking of two properties of the system that we use to consider the word random. One is the short-term unpredictability of the system, right, that we talked at the beginning of the talk. So we cannot predict what happens because we don't know all the decimal places, so we quickly lose the unpredictability, right? But this is not enough really for us to use the word random for a system. This is just unpredictable. Usually when we use the word random without maybe thinking about it, we are acknowledging the fact that this system has a long-term statistics. So you can kind of talk about probability in some sense, right? So that's what long-term statistical predictability means, right? We can talk about probability. So the important comment is that both of these can occur in deterministic system that we just saw, right? So in a mathematical model, 10x mod 1 is a perfect model that is completely deterministic, but it exhibits both of these features, right? We saw that it has short-term unpredictability, but as we saw from the theorem before, it has long-term statistical predictability, right? Okay, there's a question here that says, can this apply to other measures that may be generalized Lebesgue measure? Yes, absolutely. This result is a much more general result that applies for measures that have certain properties with respect to the dynamics called invariant and ergodic measures. So that theorem was a special case of a much more general class of theorems. Okay, so just to kind of wrap up our question from the beginning, my claim that I would like to put forward is that we should not think of determinism and randomness as opposites of each other, right? And that is why, when I ask a question about whether flipping a coin is deterministic or random, you can have lots of people saying it's deterministic and lots of people saying it's random, right? We used to think of these as being opposite of each other. I would like to claim that they're not opposites of each other. Randomness is a particular kind of deterministic system, right? And when we say that a system is, when we look at the two, at the votes for the people who said that the flipping a coin is deterministic, were focused on the mechanism of flipping a coin, right? The fact that you apply a force and you have just Newtonian mechanics that determines what happens in a deterministic way. And those that said that it's random refer to the outcome, right? That the outcome exhibits these two features, short-term unpredictability and long-term statistical predictability. Sorry. Okay, I think this is a good moment to conclude, because I know it's been an hour, it's finished. So there's some comments. Does it mean there's no randomness in long term? Does it mean randomness itself is not random? Well, I don't know what it means. It just, I'm trying to, I've been trying in this discussion to explore the meaning, not a precise mathematical meaning, but just the meaning that we associate to these terms, right? Because, and to maybe help us see that sometimes we use these words in a way that is not very thought through about the meaning, and to try to help us to understand these words in a different way, and to say that random can be seen as properties of deterministic system. I don't know if there is any system in real life that is not deterministic, that is random but not deterministic. I don't know. Okay, thank you very much.
Thank you so much, Professor. Well, the floor is open to questions. If anyone have a question, they can open their mic or from the room. If somebody want, please.
Maybe I can talk to Stefano.
Please.
Stefano, thank you very much for this interesting talk. It was really fun. So you wrote down this quote from, I think, Lagrange about the determinism. It was Lagrange?
Quote from Laplace.
Laplace. So it's a very vague statement. Does it, so what he meant by this, is it like every system can be described by mathematically some initial value problem that is will pause? That's what he meant.
So I don't know exactly what he meant, but I don't think he was trying to make a scientific or philosophical statement that the world is deterministic. I think he was just explaining what the notion of determinism, the concept of determinism means, not necessarily whether the world is deterministic or not. Right? It's just
So maybe okay. So I would assume that statement in terms of more like kind of density theorem, that deterministic system are somehow very typical among all system.
But Shah, I don't know. Is there any physical system that is not deterministic?
Okay. Okay. So physical, I don't know, but you can write down abstract L-pose problem, and to give an initial condition, you might have many solutions, and so those systems are not falling in deterministic.
No, yes, but in mathematics, you can do anything, right? I mean, mathematics, you can also, as Atik mentioned, you can say you have a random variable, you can say you choose randomly according to some probability distribution. I mean, you can define all these concepts mathematically, and they make sense, because we make some rigorous definition, we set this up, and this is very important from a mathematical point of view, and maybe it's also useful for applications and whatever, but for me, it's a separate question from, okay, is there a real life physical system that is not deterministic, right? It's not to do whether you can formulate mathematically. The richness of mathematics is that you can really be creative and do whatever you want. That's our advantage. For
It's
sure.
more like a typical physical system would be deterministic. That's what it meant.
There is, in physics, you cannot talk about a typical system. You don't have a topology on the space of physical systems in the real world, right? I don't think. The question is there any system that is not deterministic in the real world? Is that in the physical world?
Mm-hmm.
Can you give me an example?
I mean, it's a very abstract question to
It's not an abstract question, Shah. There's no question that is more concrete.
Right. So it's a question
than this.
given a physical system, and to determine whether this is deterministic or not, one has to find the physical laws to write down the initial value.
No, you don't have to. You don't have to find the physical laws to decide if it's deterministic or not. You just have to decide if the system is governed by physical laws or not. You don't have to know what they are
You
necessarily.
mean deterministic physical laws?
No, every physical law is deterministic. I mean, every physical law is, the physics. By definition, a physical law says that if you have a certain temperature, pressure, material, mass,
Yeah, I was
certain
thinking
physics,
more.
then this happens. If you drop something with a certain mass, it accelerates to a certain speed. There's a physical law, everything.
I was thinking more about this duality thing with electrons and other things. So maybe that's more confusing.
Right. Let me come back to that. First, Atik has his hand up. Let me see what Atik says. Yes.
As Shabesal mentioned that there is some system and same initial condition give different output, like which is not deterministic. I will also love to see that system if we can.
So I don't know. So I probably what you so I have asked, the natural example would be something related to quantum mechanics, somehow quantum thing, right? So I have asked some, I don't know anything about quantum, so I'm certainly not I'm not trying to make as a scientist, a statement that everything is deterministic, right? Here as a mathematicians, I say these things, but I think it's an interesting point for discussion. So I have asked some physicists, do you think that quantum mechanics is deterministic or not, right? And I've had mixed replies, right? In the sense that most people say, no, it's not deterministic. They even quote some kind of theorem, I think Bell's equation that supposedly proves that quantum mechanics is not deterministic, but I don't know what that means. And I also have heard other discussions and have read other papers that say that it is not clear, because the question is quantum mechanics, we can describe quantum mechanics best if we think of it as a random system, right? But also 10x mod 1, we can describe best if we think of as a random system, because we can prove mathematically that it has this probability, so we think of it, and in some sense the most useful way to work with it is to think of it as a random system, not as a deterministic system, but it is a deterministic system. So in quantum mechanics, is it possible that this randomness comes from an underlying deterministic system? I don't know, this is not certainly not my expertise to answer, but talking to physicists, it seems like it is not completely clear one
It's
way.
more maybe the formulation of quantum mechanics is not, something like it gives you a model that could be non-deterministic, but the actual thing may be deterministic. It could be not a good formulation.
Exactly. This is what I'm saying. It's not clear that physicists have the possibility of making a decision on that. And also, I just do not see, to be honest, in a very naive way, I'm not a scientist, I don't see how something cannot be determined by a physical law. I don't see how anything can happen without it being determined by a physical law. I don't see. And this example, I guess the point of this example is to say that in some sense you do not have to choose between the two. You do not have to choose. This example shows perfectly well that everything that we consider, that we call random, is perfectly compatible with a deterministic system. There is no contradiction at all between the two. This is, I guess, this I feel comfortable in saying as a mathematician, because I think this example, this is a rigorous statement in some sense. Yeah.
Maybe I can ask one more question. With this particular 10x mod 1 function, you could realize Lebesgue measure as a limit. But in general, it could be some probability measure different from this one, right?
Absolutely.
So what is it with this particular example that it can see the Lebesgue measure? Is it this mod 1 property or something?
No, it's the 10x property. If you think of the graph of
Mhm.
10x mod 1, it is affine. The slope is constant.
Yeah, okay.
So if you think of the graph, it's got 10 branches. If you think of the graph, you can see that the Lebesgue measure is invariant, is a technical term. But so this is a special case of much more general theory that Rizwan and I work in, which is exactly to find the limit measures of these processes, which can be sometimes just a measure Dirac delta on a single fixed point, or it can be a singular measure. There's all kinds of measures, yes.
And the limit of this sequence along this orbit doesn't not necessarily exist, right?
There are many points for which it does not exist. This would be kind of another talk, This would be what I was hinting at, but I don't think we have the time, is the notion of non-statistical, but yes, it does not.
Yeah, thank you very much.
Sure. So I guess I will leave you with that question. Maybe another time I can give another talk addressing this other question.
Well, any other question? If not, then I'll thank Professor Luzzatto for this wonderful insight to randomness and determinism. And as a tradition, we usually invite our speaker for a lunch or a dinner if they are reachable. Since you are coming to Stockholm, so me and Shah will be very pleased to host you here.
Yeah.
Looking forward to that.
Okay.